I can also prove a result for supermartingales as well. Here's an interesting small proposition. It's not a difficult proposition. Okay. So imagine I have a process. So it's about the square of a martingale. Gives you the algebra to calculate the expectation. Suppose I have a process Mn, which say belongs to L to omega. In other words, it's square integrable. Okay. Square integrable process. With of 0 equal to 0, then no matter what n you take bigger than n, if you compute the expectation of the square of the increment of the martingale, I should say it's integrable martingale. So if you can see the square of the increment of the martingale, can you see that this is increment of the martingale because you are computing the difference. Okay, given Fm, it's same as something interesting. Expectation of n square m square given Fm. Something that we wish to have a minus b square, which we can have minus a square minus b square, okay? But it happens. How can I show it? It's not a difficult thing. So the real thing is, okay, just, what do we call expand it. So if you expand this guy, mn minus m square, you will get n square minus okay, plus absolute number. For sure, then E. So the absolute of the square is same as the square actually. I can get rid of the absolute. Plus m square. Okay. Somehow this term goes away somewhere. Where does this go? What do you think? Just in your head. Just in your head, try to figure it out that why.
So if mn is equal to mn, then we'll get the same thing. It's about
If mn is
equal to mn.
Why mn is equal to mn? Right? Because it's a martingale. If you want to compute the expectation given Fm, okay, so we need to do the expectation of this expression given Fm. Okay. So what are you going to have? Okay, so I just want to keep these two terms in the expectation, and I want to just talk about this. So I have expectation of mn square minus mm square given Fm plus, not plus but minus expectation of mn expectation of Mn and M given
यहाँ पर ये प्लस होगा प्लस
सही है एम मिस का है सर फर्स्ट टाइम सर प्लस ना दो माइनस और अब कुछ नहीं था
okay, so you will have a plus. You get a minus because one will be subtracted.
Exactly.
Anyway, so what you can say about this expression? So mm is fm measurable, so I can pull it out.
सही
And mn is a martingale. So the expectation of mn given fm is going to be mm. So this is nothing but it's going to be minus 2m
M square
square.
फिर अंदर ले
We'll have expectation of m square.
प्लस M square
For example, fn plus what? M square because this is measurable here. Minus 2m m square. Okay, so you're going to get minus 1 mm square,
जाएगा
which you can return back basically inside expectation.
बात करने के
This would be a useful property. The last result for this section, and then we can do the break and start afterwards. But the next result that we will do is a pretty popular result, especially in continuous time case. It's called the Ito Isometry. Okay? It's called the Ito Isometry, but here we will do a discrete version of Ito Isometry. So these are the tools which are important. We will do them at several instances. Okay? So let's try to do Ito Isometry. So, for Ito Isometry, or you need to assume, so imagine you have an square integrable process. Xn is square integrable. Square integrable. Okay. Right. Aforementioned. Let me recall what is stochastic impact. Discrete stochastic impact because I'm using that as. So recall what was discrete stochastic integral? For discrete stochastic integral, we must have a martingale, okay, and a predictable process. Then, if I, define Xn as j goes from 1 to n,
HJ
Hj, Hj times
MJ minus NJ minus
j minus
NJ minus 1
So recall, what do you call, a discrete stochastic integral. If you have a martingale and a predictable process, using this martingale and a predictable process, you can define roughly discrete integral of the predictable process with respect to the martingale. If I want xn, for example, to be square integrable, okay, square integrable. In other words, I want that the expectation of xn square must be finite. Then what assumptions should we have on h and m? So one of the possible assumptions that you can have on h and m is that assume that hn is bounded. Okay. So if I assume hn is bounded and assume that mn, for example, is say square integrable, then you expect xn to be also square integrable. Assume it to be square integrable. Now, under what condition this could be square integrable? There can be many conditions actually. This is just one of them. Okay, this is just one sufficient condition that this is square integrable. But it doesn't mean that that's the only condition. We can have other conditions to it. Okay? So this is just one example that h and m should satisfy in order to have the square integrability of a process xn. But you can have other conditions. So now I like to write what do you call the Ito Isometry. Okay. And it's really an isometry actually. Makes no sense. Okay. So what does this say? So it says, imagine this discrete stochastic integral is a square integral. Okay? It's square integral. Why it's a square integral? It could be due to whatever reasons, okay? You know, maybe hn is bounded, mn is a square integral, or maybe due to some other reason, but it's a square integral. Okay? What was the point of showing this? That, you know, that assuming square integrability, you know, it's not an alien thing. There are situations where you can have this square integral. Okay. But here I'm assuming the abstract square integrability. In other words, I'm not assuming that hn is bounded and mn is square integral. For now, I'm not assuming it. If I'll need, I'll assume it. For now, I think we don't need it. Then you can do what? Then if you compute the expectation of xn square, process, what you can do is the sum of j equal to 1 to n h square k times k minus k minus 1, okay, where this process an is compensated for n square.
xn is square.
M is square. I know mn is a martingale.
And hn is
Mn square is not a martingale. It becomes a sub-martingale. So if it is a sub-martingale, it is going to have a compensator.
right.
Okay. Then what does this result is telling you? That if you compute the expectation of the square of this body, okay, this is going to be same as the expectation of what do you call the square of the h times not the increment of the martingale or the square of the martingale, but the increment of the compensator actually. So if you interpret this, so here on this side, you have roughly a stochastic integral. Stochastic integral. In other words, integral of h with respect to the martingale. But if you see this side, you can treat this as that you will see it in the continuous time case actually, that this becomes a Riemann integral of what do you call square. So somehow that martingale that was presented there just goes away. How can I show it? So first I need to compute the xn square and then take the expectations. So what would be xn square? Xn square is if this sum of hj mj minus mj plus and square j equal to 1. So how can I expand this sum? How can I expand this sum? So I can use, not using the bookish way, I can use this form. So if I have, let me give you a just link that if you have a plus b plus c square, what do you get?
A square plus
But instead of if I have a1, a2 and a3, what would be the best way to write it actually? Just to make you realize, you know that you're going to have a summation I equal to 1 to n ai squared. Right? Plus 2 times of, then I have a double sum. But I can write that double sum in this as a single sum roughly in this way. Then for every I less than j means for 2 different indices you should have ai j. Is a clever way of doing it? Let's do the same with that. We're going to get j equal to 1 to n h j square mj minus 1 square, okay, plus 2 times of the long expression. There is always a lot of learning in going through such expressions. Okay. So plus 2 times of the sum, it's basically a double sum. I less than j of what?
H I is j.
H I Hj
Times.
okay, times product of Mj minus 1 times Mi
Minus mi minus
minus 1 actually.
1.
And now I would like to do what? I would like to take the expectation. Take the expectation. Expectation of some is expectation. Basically, this is what that we require to keep it. Because think about it. That's j square and is it? I should write. There's no square so a. What would be mj minus 1? We'll see that. Times the expectation of. So, not going through the bookish way. Let's hope that we will reach some yet. So you have expectation. I can really insert this expectation inside. Now let's think about this expectation explicitly. Okay. Okay. So let's call this a star. Let's call this function as a star. So the expectation of Hj times Mj minus 1 and Mi minus Li minus 1. Okay? Consider this expectation. I wish to be 0. I wish it to be 0. Because once it is 0, this gives me what I want. Okay? So let's see that why this is 0.